Hello everyone, we're at Team Vicor and this is our project, the Low-Cost Desktop Design Evaluation System. Our technical directors are Senior Principal Design Engineer Christopher J. Sanzo and Principal Design Engineer Andreas Ladas, and the team's Consulting Technical Director is Mike Smith, founder of Bold Circuits, all URI graduates. My name is James Gannon and I'm an electrical engineering student here at URI, and I'm joined here by Nathan Shake, also electrical engineering, and Brady Peacock, computer engineering. Vicor Corporation is headquartered in Andover, Massachusetts, and develops modular power components and complete power systems for the aerospace and defense, automotive, and high-performance computing industries, just to name a few. A cluttered workstation like this is anxiety-inducing to say the least, and it's easy to find in the testing environment. We've all come across a setup like this at one point or another. A lot of applications and testing engineers often find themselves trying to use many different devices at once at the lab bench, each of which being expensive and non-portable. Our intent is to force and sense voltage and current at high precision for integrated circuit or IC testing purposes. And this setup is generally what it takes to do this. So what if there were a way to pack all of this testing equipment down into a low-cost portable solution that can achieve the same high precision results? Our team set out to prototype this all-in-one solution. Our goal was to develop a one-plug, sub-$5,000 desktop-sized evaluation system to force and sense currents and voltages across a device under test, or DUT, that is completely controlled using a Raspberry Pi. The team was tasked with building a 2-channel force sense unit that interfaces with a 48:1 multiplexer in order to individually select each pin on the DUT, as well as creating a well-documented application programming interface that allows the user full control over the system by performing basic functions in order to create measurements tests on the DUT. Although some technical milestones were adjusted along the way, the anticipated best outcome was achieved during this project. We were able to design a custom 2-channel FSU PCB, as well as achieve desired results during a series of measurement tests using stand-in hardware with slightly less accuracy compared to the custom PCB. Additional testing must be done to bring these two achievements together, as the custom FSU PCB has yet to be interfaced with the system. After assembling the prototype solution for a more condensed, one-plug precision IC testing system, the company is on track to producing a compact, force-sensed unit capable of reducing overall testing system cost, increasing IC testing efficiency, and freeing up real estate in the lab. Here is an overall block diagram of the project, and I will be explaining the FSU section of the diagram. The team was able to transition last semester's FSU breadboard design to a printed circuit board leveraging Circuit Maker as our main design platform, which uses tools similar to Altium. Many key PCB layout skills were learned during the design process, including analog circuit fundamentals, circuit protection, Kelvin sensing principles, and parasitics. The more copper traces present in the design, the more likely the chance of increasing unnecessary intrinsic resistance in the system. Since our goal is to design a high-precision system capable of sensing test currents in the nanoamp to milliamp range, we want to minimize as much of this resistance as possible. On the left, we have our system output line in yellow, which must run through the bottom of our sense resistor network shown in green, incurring extra resistance along the way while sensing upstream. We fixed this by using a downstream sensing approach where we could sense a particular resistor without incurring the summed resistance of extra resistors that lie ahead in the network. I'll now hand it off to Nathan, who will touch more on the process of creating our system.
As James talked about the PCB layout of our FSUs, I'll talk more about getting to that step and also the MUX cards that we used. Before being able to get to the PCB layout, we first had to translate our circuitry and simulation into a schematic form. This was a very crucial step. As we were using Circuit Maker, the program is able to link up the schematic and PCB together to be able to verify our design. One of the biggest things I learned this semester is how important consistency is. If your schematic doesn't match up to the layout or the circuit, or even just slightly off, things are going to go the wrong way. We found this out very quickly when we were trying to reference between the schematic, the initial layouts, and the simulation circuit, finding that they didn't line up. Although it didn't cause any major issues, it still proved to make the process a lot longer than it needed to be. My focus this semester was mainly on schematic design and the very initial placement and the layout of our PCB. I was able to learn a lot about schematic design this semester. Since we were designing a 2-channel FSU, there were a lot more components that needed to be used compared to our circuit last semester. To combat this, we needed to introduce a hierarchical design consisting of multiple layers to be able to fit everything and make it understandable. In addition to the basic circuit that we had previously designed, we also had to put in a lot of thought about the protection of our circuit. Since when using breadboards, you have a lot more control over the circuit, but in PCB design, once everything is set in stone, there isn't much you can do about it. So we really had to look at bypass capacitors and protection diodes to ensure that things didn't get out of hand. Although the FSU card is the main target of the project this semester, it wasn't the only card I worked on. The other card that I worked on was the MUX card. As our goal was to be able to address the 48 different pins on the board, we needed a way to access all of them from a singular point, as there was only a singular FSU output. The initial design of the MUX board was a bunch of MUXes on it. This provided us with the bare minimum of what we were looking for. However, it proved difficult to be able to control all of the MUXes at the same time. To combat this, the addition of a DMUX or digital MUX was implemented to be able to reduce the needed amount of control inputs. However, due to the nature of the DMUX chosen, it gave us the opposite signals of what we wanted. So to fix this, we needed to add inverters to be able to give us our wanted signals. Once the vector board was understood and working as intended, I moved on to implementing it into a circuit maker in a schematic form to be able to have it eventually fleshed out onto a PCB board. The goal of this was to upsize and increase the amounts of MUX boards, as we would need 2 per FSU channel, 1 for force and 1 for sense. Since the design was going to need 4 MUX cards, it warranted a better form of control over all the MUX cards, as the amount of control inputs were getting out of hand again. To fix this, the inclusion of an I/O extender that would allow all the MUXes to be controlled from 2 points, massively reducing the amount of control inputs needed. Thus, we had our goal of a schematic with 4 MUX cards that would connect to each of the pins and allow us easily control of which FSU outputs go to where, and be able to choose which pins are sensed and have it almost ready for PCB layout. So with all the physical components out of the way, here's Brady to talk about the side that controls our system.
To put everything together, a quick recap from last semester's presentation. The Raspberry Pi is controlled by the user and sends commands over to the Arduino. The Arduino handles communication with the DUT, DAC, and ADC, as well as the enable and select pins on the MUX cards through GPIOs. The DAC controls the input voltage to the FSU, while the ADC reads the output voltage from the DUT. On the computing side, the main focus for this semester was API development. Last semester, we got the ability to program our board, but it was a fairly convoluted process, so we wanted to streamline this process and make it more accessible. We implemented the following commands shown on the slide, which perform the most basic and low-level functions of our system. This gives the user the foundation and building blocks to create something more high-level to perform any sort of measurement on the DUT that they wish. We've also provided a very simple example on the right side of the slide, just to showcase the API a little bit. This example simply moves a voltage of 2.5 volts onto pin 39 of the DUT all through channel 0 of the FSU. The first 2 lines seen are required of any script using the API. It's just importing the library and setting up a connection with the Arduino. The next line shows the select DUT pin command, where you specify the FSU channel that you wish to be accessing that pin, channel 0 in this case, and then the pin number itself, 39 in this case. Then finally, you would call the force voltage command, also specifying the FSU channel, which is again 0, and the floating point value of the voltage in the range from 0 to 5, in this case 2.5 volts. As you can see, it's very easy to read and almost reads as plain English, so this in turn makes it easy to program as well. Finally, we worked on some measurement scripts that used this API. This would prove the fruits of our labor, showing that we are able to use our system to perform useful tests on the DUT in a way that is easy to program. So here's an example of one such script, as well as the output of the script that tests a comparator on the DUT. The chip we tested has a comparator on pin 37, which monitors the voltage on pin 39. Pin 37 is low until pin 39 hits a certain threshold voltage, in which case pin 37 is then set high, indicating that the threshold has been reached. Running through the script, first there's the connection we mentioned earlier, and this will log some initialization messages to the console, and obviously if initialization fails, it will tell you there. Then we program the dot via I2C commands, basically just activating the comparator and setting the threshold voltage. Then we set FSU channel 1 to pin 39 that we mentioned, and FSU channel 0 to the comparator on pin 37, showcasing the usefulness of having multiple channels, because otherwise you would have to keep switching the mux back and forth between these pins if you only had one channel. Finally, we have a voltage sweep starting at 1 volt. We use the API to force voltage and measure the comparator pin at each step. Once it detects the comparator has been switched, meaning the threshold has been reached, the loop breaks and records the voltage at which this happened. In this case, it was at about 2.4 volts, as you can see in the console output at the very bottom, and this matches the settings that we applied during the I2C commands above, verifying the functionality of the comparator and thus passing the test. All in all, we have created a force sensing system capable of performing full characterization measurements on a device under test, with an easy-to-use and well-documented programming interface. With that said, we would like to acknowledge and thank everyone who made this possible. Thank you to our technical directors Chris, Andres, and Al, our consulting technical director Mike Smith, and of course, Dr. Sunak.